Okay, so I'm going to be introducing more topics about laser theory, focusing on fixed atomic population and a quantum model. So first,
I have immediately the question. So it looks like before it was also laser theory.
Yes, mine was classical, his is quantum.
Yeah. So quickly, just to briefly overview why we want to model lasers is so we can increase their efficiency, so we can maximize the population inversions, get different wavelengths, maximize the brightness, and minimize how much energy we have to input. And so whenever we want to apply these models to real situations, we have to have spectroscopic measurements for whatever our active medium is, so we can know their, so lasers will work. There we go. Okay, so we can know their energy levels and the lifetime of the states, so we can model the rates. And then we need to have a model of our pumping method. So usually it's either electrical or optical. The basics, we've already talked about pumping, so I won't get into that, but we also have an active medium, and that's just whatever our atoms or molecules are that we're exciting. So we place these into a cavity, which I think I missed the part where Stephen was talking about what the cavity is there. It's just so we can contain all the light, so we can only direct it out into one direction. So I do want to make a correction to this. Ignore the second line. I was thinking about this while the presentations were going, but so increasing the intensity of pumping will create a faster population inversion, but also based on the idea of detailed balance, having a higher rate will also increase the overall population of our excited states. And then finally, we have simulated emission. So going back to detailed balance, the whole idea of detailed balance is that the population and equilibriums are based on the rate of absorption and emissions. So from that, we can establish this equation where we have the excited state rate of change is equal to the inverse of the negative of the ground state change. And so we can adapt this to a multi-level model with n energy levels. So it's not just a two-state system. And we have this function where P is the probability of a state n's occupancy. So n is just a quantum number corresponding to our states. And then P, since it's the probability, we can also liken it to the density matrix operator.
And get N2 and N1, number of, what is N2 and N1?
Oh yeah, I was going to talk about that here. So N2 and N1, N1 is the ground state, just ground state population. N2 is any excited state population. So it can be the first excited state or higher. And so when we generalize it, N2 will represent all of the excited electrons or excited atoms. And so we generalize it to get this equation of motion, which is all based on the equation of motion for the ground state. And we can normalize, we're using the normalization factor, we can get the value for that. And so the probability of state n being occupied is given by this function. And then more importantly, we get the mean chaotic photon number, which is this, which is just a ratio of the all total excited state occupancy over this ratio, I guess. And going back to chaotic photon number, this is a bit of a new term. I've never heard people talk about chaotic light, so I had to do some research to figure out what that was. So chaotic light is just photons occupying the diagonal in our density matrix. So it's observable values, and they are non-imaginary. It should say coherent light. That's what the word is blocked. But coherent light is going to be occupying the off diagonals. So there's going to be imaginary parts. So we can think about it as, if we think about the labs that we did, the coherency terms were occupied during transitions. So we can think about this light as transitory light. And back to the magnet analogy, which I'll talk about again in just a moment, we consider everything as a single electronic mode where everything is combining into a total wave function, but each particle contributes its own wave function. So yeah, we consider it just one whole wave function. And this figure is just describing how if we have some kind of pumping that we do at the beginning. So if we start here, we start at a higher ratio of ground state to excited state. Over time, we decay back to a standard. And so if we have fixed atomic populations, we'll always go back to our equilibrium. So in our quantum model, as Stephen set me up for, we do the analogy to magnetization. As we talked about, in magnetization, we have a bunch of particles that all interact with each other based on their dipoles. And we have temperature, which is analogous to population inversion. And since each of these dipoles interacts and affects each other's dipoles, so they're all coupled, this is very similar to electric field and a laser. So we can model electric field in the same way to magnetization. So we use the self-consistent field method, or I think it's also called Hartree-Fock, which is where we just take each individual particle, calculate a one electron wave function for just that one particle, imagining it's not interacting with anything else. And then we do a Slater determinant of all these wave functions to get one total wave function, which is based on all these one electron systems. And then we plug that into or use that determinant with a multi-electron Hamiltonian and get a decent approximation for the actual values here. And so using this method, we get the probability density for magnetization, which is this function, which is very similar to the probability density for electric field. It's identical in form. And so in this function, instead of using magnetization energy, we have free energy from our electric field, which is G given by this long function. And instead of over KBT, we have K sigma, where I said sigma is our population inversion, and then K is just a factor of the gain, and N is the number of atoms. So another system I wanted to mention is just the 4-state system, because this is a 3-state and 4-state systems are essential for most laser operations. What's nice about the 4-state system is that we have enhanced lifetime because of a intersystem crossing. And so we have decay rates that we have to model for. And so we can have our population. This should be rho EE, one mistake just based on typographical errors, I guess. But so rho EE is modeled by the pumping rate, spontaneous decay, and Rabi oscillations. And our ground state is also like this, but more focus on the excited state. And so population inversion is just going to be the difference between our excited state occupancy and the ground state. What's really important from this function is this ratio 1 over gamma and 1 over gamma G. So gamma is the decay from our second excited state back down to its second ground state. And then gamma G is from ground back to original ground. And so if our lifetime of this excited state is greater than the decay rate from here, we can have a population inversion over time as our pumping is doing more work than the decay is. And then we can quantify the polarization, which will indicate how strong our electric field is over the cavity of our laser. And we also include B, which is our saturation, as Stephen mentioned earlier. And that's all I have to talk about.
Okay, good. It looks like you are the champion of one, the champions in